Swayam Prabha. Digital India. Educated India.
Alright, let's start our discussion of caches. So caches are very interesting and there's a huge amount of research on how to make caches efficient. So we'll not be able to cover most of it in this lecture, but at least we'll be able to cover most of the basic mechanisms that underlie today's modern caches. So the overview of a basic cache is as follows. It's a black box. Let's first treat it as a black box, as a memory that contains a set of memory addresses and their values, arranged into blocks, of course. So for blocks, you need to go back to the previous lecture. So what we had discussed in the previous lecture is that the memory system is organized hierarchically. So we have an L1 cache, which is small and fast. Then we have an L2 cache, which is slightly larger and slower, and finally we can have an L3, or we can have a main memory which is made of DRAM cells, right, which contains all the addresses. And so this addresses in L1 are a strict subset of the addresses in L2, and addresses in L2 are a strict subset of the addresses in main memory. So we had discussed that, and also to take advantage of spatial locality, right? Because having a cache hierarchy takes advantage of temporal locality. So to take advantage of spatial locality, we had discussed grouping memory addresses into blocks. So if we group them into blocks of 64 and fetch a block in one go from a lower level, right? A block is an atomic unit, so we never have half a block or a third of a block. So you fetch a block in one go, so most likely if you're accessing, one data item within a block, most likely we'll be accessing in the near future some other data item which is also within the block. Since that has already been fetched, we don't have to fetch it once again, so this will increase our cache hit rate. So any cache can be looked at like this, that we have a memory address that goes in. So if it's a load, then a load value will come out, and also a hit or miss decision. Of course, if there's a miss, the load value does not make any sense. Right? So for a load, basically we have an address and a value. For a store, same way, if the block is not there, we'll have a miss. But if the addresses of the block are there, we can perform a store. So a store will only have a memory address and a store value. So for a store, a load value makes no sense. So what are the basic problems? We need to make a hit or miss decision first. If there is a cache hit, we need to perform the load or store. So let us look at the basic cache operations and describe the operation of an entire cache on the basis of some of its primitive operations. So the first operation, let me move to a laser pointer. Yeah. So the first operation is lookup. We check if a given memory location, a given memory address is present inside the cache, right? That's the first thing that we check. If it's not present inside the cache, well, we declare a miss and we just move out. But if it is present inside the cache, then we can do, several things. If it's a load, we can read data from the cache. So it's a data read operation. If it's a write, we can do a data write operation. We can write data to the cache and we'll be done. Now assume that there was a cache miss, and then the block comes from the lower level. Then we need to insert the block inside the cache. And to insert a block, sometimes it might be necessary that we might find that the cache is full. So then we have to throw out one block. So we need to first find a candidate for replacement. Then we need to evict it, throw a block out of the cache and insert the new block in its place. So these are our 6 basic operations: lookup, data read, data write. If there is a miss, we need to do insert, replace, evict. These three operations need to be done. So we shall look at each of these operations in great detail now. So let's first define a running example. So we will pretty much devote at least this entire subsection. This entire subsection will be using this running example, because having some example sort of streamlines our thinking. And instead of using symbols, it's better to use a concrete example. So let's try to design an 8 kilobyte cache with a block size of 64 bytes and a 32-bit memory system. Alright, so what again is the configuration? It's a 8 kilobyte cache, 8 KB, block size of 64 bytes in a 32-bit memory system. Furthermore, inside the cache, let us have two SRAM arrays, two arrays of SRAM cells. Let's have a tag array which saves a part of the block address such that we can uniquely identify a block. So a tag array just contains a part of the address. And let's maybe discuss block address slightly more before moving to the block array. So a block contains 64 bytes. So 64 bytes is 2 raised to the power 6 bytes. So since a block is an atomic unit, we will never partition a block. So in a 32-bit memory system, how many possible blocks can we have? It will be 2 to the power 32, because that is the total size of the memory space, divided by 2 to the power 6, which is the block size. So maximum we can have 2 raised to the power 26 blocks. So a block address is 26 bits, right? A block address, because 6 bits are taken away by the address of the byte inside a block. So the maximum number of blocks we can have is 2 to the power 26. So a block address at the most is 26 bits, which means that we need 26 bits to uniquely identify a block. So let me go to the block address and just add 26 bits here, right? So mind you, if I change these parameters, then these parameters will also change. But let's at the moment discuss everything in the context of a running example. So then we have, along with the tag array, we have a block array which saves the contents of the block, right? So the contents of the block, how large is it? The contents are 64 bytes. There's one block we have defined to be 64 bytes. It saves the contents of the block. So both the arrays, the tag array and the block array, need to have the same number of entries. And in fact, they can have a one-to-one correspondence, right? So they absolutely need to have the same number of entries. All right. So the structure of a cache is now as follows. We have defined two arrays, a tag array and block array. Of course, they are not drawn to scale. And they have the same size, the same number of entries. Both of them exchange data with a cache controller, which is a piece of logic that controls the cache. So the cache controller gets the address, in the case of a store, the store value. It interacts with both the arrays. It has two outputs. One is a hit-miss decision, and other is a value of a load if the operation is a load operation. So let us discuss one of the simplest kinds of caches called a fully associative cache. So let's do a little bit of math. So our cache size is 8 kilobytes. So let's try to find out how much this is in bytes. So it's 2 raised to the power 3, which is 8, multiplied with 2 raised to the power 10, which is so 1 kilo. So 1 kilo means 1024, which is 2 raised to the power 10. So this 2 to the power 3 times 2 to the power 10 is 2 to the power 13. Alright. So this is the number of bytes that we have in our 8 kilobyte cache, 2 to the power 13. And since one block is 2 to the power 6 bytes, 64 bytes, so what is the maximum number of blocks that we can have in the cache? 2 to the power 13 divided by 2 to the power 6, which is 2 to the power 7. So 128. So we can have 128 blocks, so the cache will have 128 entries. Alright? So in this case, in a fully associative version of our cache, we'll have 128 entries. So 128 entries in the block array, 128 entries in the tag array with a one-to-one correspondence. And in a fully associative cache, if we have 128 entries given a block, it can be stored in any entry. Alright, so given a block, it can be stored anywhere inside the cache, in any of the 128 entries. So recall what we have done in the previous slide. We have said that we can have 2 to the power 26 possible blocks. The reason we said that is basically because we have a 32-bit memory system and a block size is 64 bytes. So 2 to the power 32 divided by 2 to the power 6 is 2 to the power 26. So a block address is 26 bits. Right? And then since a block is 64 bytes, which is 2 to the power 6, so there's a 6-bit offset of a byte inside a block. So let's do one thing. Since a block address is 26 bits, let's save the entire 26 bits in the tag array. So we will require it, but let's try to understand this gradually. So in the tag array, let us save 26 bits, which is the block address. Alright. So, we'll have different sets of 26 bits for different entries. And in the data array, we'll have the contents of the block, which is essentially 64 bytes. B for capital byte, capital B for byte, right? So what we see over here, the way that we do the addressing is that given a memory address, we first compute the tag part of the memory address, which is the upper 26 bits. And then there will be a byte offset part, which is the 6 bits. So where does 6 again come from? It comes from the fact that 2 to the power 6 is 64 and 64 bytes is our block size. So these lower 6 bits we will ignore. We'll take the upper 26 bits, which is this tag over here, and we'll compare them with each of the entries of the tag array. Right? So with every single entry of the tag array, we will compare the 26 bits, the more significant 26 bits of the address, to find out if there is a match. Alright, so because this is the block address inside the address, so we'll compare each of these 26 bits with the 26 bits stored in the tag array. So mind you, what are these 26 bits? They are the addresses of different blocks. So address of block 0, right, the block address of block 127. Now when we are being given a new block address, we need to check with each one of them. And so for this, the best structure that we can use is a CAM. Recall from chapter 6 that a CAM is a content addressable memory, where instead of accessing the memory via its row address, we access it via its contents. And this is an ideal application of a CAM, where given the block address in the address, given the block part of the address, which is also called the tag part, we compare the 26 bits with each of the 26 bits stored here. And so this is done in a typical CAM array. And after each comparison, we send them to an OR gate. So if, let's say, so since there is no duplication inside a cache, if there is a hit, it will hit in only one entry. So let's say it hits in this entry, so this will be 1. So the output of the OR gate is 1. So if this output of this OR gate is 1, it means that there has been a hit. Otherwise, if the block address does not match any of these entries, any of these tag entries, then it means that there is no hit and there is a miss, right? So basically, if there is a hit, the OR gate will give a 1, which means there has been some match here. Otherwise, the OR gate will yield a 0, which means there has been no match. After that, if there is a hit, only one of the lines will be 1. To get the address of that line, we'll use an encoder, which will tell us, in this case, what is the address of that line. And this will be a 7-bit address because there are 128 bits here. So this will be a 7-bit address, right? Which line actually hit. And the data array will be a regular array of SRAM cells. All right. A simple regular array of SRAM cells, nothing very sophisticated about it. So let's say there is a hit in, so this is 0, 0, 0, 1 and 1, 0. So basically it's the second entry in which we have had a hit. So we'll go to the second entry of the data array, read the data, and that will be the output. So if it's a load, the output is the 64 bytes or any subset of this. If it's a store, then we'll essentially write to this entry. So in any case, we are doing lookup. So our aim of the lookup stage is to indicate in which entry of the data array does the memory locations value exist. All right. So let me just quickly summarize what is a fully associative cache. In a fully associative cache, the block can reside within any entry of the cache. So we did some amount of math, and from that we figured out that we will have 128 entries in our cache. So in this case, the block can reside in any one of the entries. Now, if the block is residing in any one of the entries, how do we know which one? So for a lookup operation, so let me, okay, I think let me clean up a small part of it and such that I actually ended up erasing all of the text on the slide. So that's okay. Let's just abstract the problem. So let me maybe move out of PowerPoint. So the problem that we have at hand is that we have a cache with 128 entries. Right? So a block comes, an address comes. An address is a 32-bit quantity, and we need to map. I can maybe change the, okay, fine with the color. So what we need to do is that we need to find out this address, where exactly this address is contained within the cache. So what we do is that we consider the 32 bits and we try to break the address into two parts. One part is the offset of the byte within the block, and the other is the block address. So since a block is 64 bytes and 64 is 2 raised to power 6, this means that the first 6 bits represent the address of the byte within the block. So this is something that we can ignore or discard. The remaining part, which is the next 26 bits, is what constitutes the block address. All right. So this part is the block address. Right, the 26 bits. And so what we need to do is that we need to find out which entry out of these 128 corresponds to the block address, which is represented by these 26 bits. So this cache can further be divided into two parts. One is, I think this is fine. Sorry. Yeah, medium. So one is a tag array. And the other is a data array. All right. So basically the tag array contains a portion of the address such that we can uniquely map the block. So in this case, since the block can be present in any entry, the tag needs to contain the block address for the entry that it corresponds to. So recall that both the tag array as well as the data array will have 128 entries, right? Both of them will have 128 entries. So, and there is a one-to-one correspondence between a tag entry and a data entry. So what we need to do is that uh, we need to compare each tag with the block address, which is 26 bits. So the tag also needs to be 26 bits because it also needs to contain the address of the block whose contents are in the data array, right? So we compare the block address that we get, right? The block address that we get with each and every entry of the tag array. If there is a match, we figure out for which entry there is a match. So assume that there is a match for this entry. Then we access the corresponding entry in the data array and we return, if it's a load, we return the contents of the data array, which is 64 bytes, out of which we can choose a subset. Or if it's a store, then we write to the relevant portion of the block inside the data array. So the basic problem here is essentially a search problem. That given 128 entries in the tag array, we need to find if any of the entries in the tag array matches the value of the block address. If it does, we are done. The way we do that is basically via the CAM array over here. So recall that a CAM is a content addressable memory. So the block address, so the block address is essentially the tag part of the address. This thing is compared with each and every entry stored in the tag array till so we either, if we don't find an entry, it's a miss. If we find an entry, so we'll never have duplicates, then we access that entry of the data array. So this is called a fully associative cache. Well, where does the name come from? The name comes from the fact that a given block can be associated with any entry in the data or tag arrays, which means it's completely or fully associative. So that's where the name comes from, right? Can be associated, so associative. And in particular, it's also called a 128-way associative in this case, because there are 128 entries and any entry we can map. So we'll anyway discuss about ways later. But the basic idea always in the lookup stage of any cache is the search. Once we do the search, we can progress to the next stages. All right. So basically, this slide essentially discusses much of what we have talked in the previous slide. That in the CAM, it summarizes what the CAM array, the tag array does. And for any doubts on how a content addressable memory works, readers can go back and refer to chapter 6, the chapter on digital logic, right? Where we discuss registers, memories, and logic. So that chapter. Now let us discuss a very different kind of cache. So what was the problem with CAM arrays that we talked in chapter 6? So one problem was that CAM arrays, instead of a 6 transistor cell, they have a 10 transistor cell, and so they are larger. As a result, they're slower, and also they are not power efficient at all because we need to compare the block address with every single entry of the tag array, which is not power efficient by any means. So let's look at a different part of the spectrum. So let us have a cache again with a tag array and the data array, but let us divide the address in a different manner. So if you consider the address, the lower 6 bits will always remain the offset within the block. So this is something that we can happily ignore. But for the upper 26, let's divide them into two fields, a 19-bit tag and a 7-bit index. So 7 bits means it can uniquely address 128 entries. So let us use this index to map to only one element of the tag array. So direct mapped cache means that a given block can reside in only one entry of the direct mapped cache. Unlike a fully associative cache where it could reside anywhere, this can reside in only one entry. And how is that entry decided? We basically remove the remove the block part, the block address part, which is 6 bits in this case because it's a 64-byte block. We take the remaining 7 entries. Why 7? Because our tag array has 128 entries and 128 is 2 to the power 7. So we take the remaining 7 entries, we compute an index. With that index, we access the tag array and we read the tag that is stored and we compare that with the tag part of the address, right? If the comparison results in an equality, well, it's a hit, otherwise it's a miss. If it's a hit, then with the same value of the index, right? There's a one-to-one mapping here again. This we have located the block inside the data array that we need to either read or we need to write to. So what's the advantage of a direct mapped cache? The advantage of a direct mapped cache is as follows, that it is very simple. Unlike a fully associative cache, it is very simple. We don't need to use cams at all. So the tag array can be an SRAM array. Right, so both the tag array and the data arrays can be an SRAM array, right? Array of SRAM cells. And both of them also in this case will have 128 entries, but it's just that a given block cannot reside anywhere. It has a fixed place. And the place is decided by the lower 7 bits, the least significant 7 bits of the 26 bits that remain after the 26 bits of the block address, the erstwhile block address. So this is a nice simple circuit. SRAMs are much faster than CAMs. So it's a very, very simple circuit that can be used. But it's just that it's also faster. So a direct mapped cache is also faster than a fully associative cache. The only problem is that it will have a lower hit rate. And the reason being that assume that there are two lines. So a block is also called a cache line, right? So a block is also referred to as a cache line. So a block, well, we'll use both the terms interchangeably. So assume that two cache lines map to the same entry. All right. So if they map to the same entry, then what will happen? They will just be displacing each other, and that will lead to a lower hit rate or a higher miss rate. But had this been a fully associative cache, they would have found space within the cache, and one could have maybe resided here and another could have resided over here. But in this case, since multiple conflicting lines or cache blocks can reside in the same entry, we'll have more displacement from the cache, and as a result, a lower hit rate. So let us now look at something which is in the middle. And so this slide I'm not going through because we have just discussed the operation of direct mapped cache in the previous slide. So without any further discussion, I'll just move to the next slide, which talks about an intermediate solution called a set associative cache. So what was our assumption in a fully associative cache? That a line can reside in any of the 128 entries. For our running example, of course. For a direct mapped cache, we said a line can only reside in a particular specific entry. Well, so in a set associative cache, what we will do is that we'll make sets of, let's say, 4 entries. So let's consider 4 entries. So we will call them a set, right? A set of 4 entries is a set. So what we will do is that if we create such 4 entry sets, how many sets will we have? We'll have 128 divided by 4. 32 sets. So the logic is as follows. That we first, we'll consider the block address part, the part that determines the addressing of the block, and the lower 6 bits, of course, we will discard. Then since we have 32 sets, we'll first take the lower 5 bits of what's remaining, and 2 to the power 5 is 32, so just so that we have our discussion in the right context, we will use the lower 5 bits to first index and access the right set. Once we access the right set, we'll find 4 entries over there. Inside the 4 entries, we'll compare the block address with each of these entries. And wherever there is a match, if there is a match just among these 4 entries, then we'll declare a hit, otherwise we'll declare a miss. So what's the basic idea? The basic idea is that this is a solution which is in the middle of the spectrum between a fully associative cache and a direct map cache. So in a fully associative cache, our choice was, okay, let's talk about the cache type. And the choice, right? In a fully associative cache, we had a choice of 128 entries. So a block could be there anywhere. In a direct mapped cache, we had a choice of only one entry. In a set associative cache, our choice in this case is 4, which means that the line can be anywhere in a set of 4 entries. So in general, we can define what is called a k-way set associative cache, where k is the number of entries in each set. So instead of 4, it will become k. So this particular example is a 4-way set associative cache. So if you want me to explain it in a different way, I can do that as well. So let me just clean up the ink on this slide. So what we can do is we can take all the 128 entries and we just have to group them into entries of 4 each, right? Create such kind of, right? So if this is the tag array, so the data array remains exactly the same. There is no difference. Data array remains the same in all the caches, more or less, in both direct map, set associative, fully associative. The data array remains the same. It's only the tag array which we change. So we will first create 32 such sets where each set contains 4 entries. Now let's say we take a block and we read its 5 index block. So index is the set index. So we read its 5 bits after discarding the lower 6. So let's say it points to this set. After this, we compare the remaining part of the address because these 5 are fixed, right? On the basis of these 5, we have come to this set. So we need not consider it anymore. Then we consider the remaining part, which is 21 bits, right? The block address ideally was 26, but out of that 26, we took 5 out and we used those 5 to access a set. So all the entries in the set will have those 5 bits in common, so we need not store it. We take the remaining 21 bits, and so here we have a 21-bit tag, and we extract the 21-bit tag from the address as well, and we just compare with each and every entry in this set. What do we compare? We compare what is stored in these entries and the tag part of the address, which is 21 bits. If there is a match, we declare a hit, otherwise we declare a miss. And furthermore, if there is a hit, then we find where there is a hit and read the corresponding entry from the data array. So there is a nice diagram over here. So what the diagram says is that we first consider the address. So the address will have the lower 6 bits will be the block address. I'm sorry, lower 6 bits will be the address of the byte within the block. So that is something that is discarded. Then we take 5 more bits. So that is the set index. And using the set index, we access 4 entries of the set. And we take all four entries and compare that with the tag part of the address, which is 21 bits. So we do four comparisons. So this can be an SRAM array. It does not have to be a CAM, so it can still be fairly fast. So we compare the four entries, the four tags that are stored here with the tag part of the address. And after comparison, we send the results to an OR gate. So if any of the comparisons was successful, it means that the data is there in the cache. So we can declare a hit. Otherwise, we declare a miss. And furthermore, the encoder tells us that there was a match in which entry, right? This one, this one, this one, or this one. And then what needs to be done? Well, what we need to do is that we need to take the four indices inside the tag array and we need to choose one of them because one of them must have matched. So let's assume it is this one. So this one will flow via the multiplexer to the entry in the data array. And this one actually corresponds to this entry. Right? Okay, so basically, uh, yeah, so basically it corresponds to this entry, and we'll go to the corresponding entry in the data array, which is this one. If let's say we had a hit in this entry, then we would have gone to another one. So it doesn't matter, right? The what we need to remember is that each entry in the tag array has a corresponding entry in the data array. There's a one-to-one correspondence. So what is the new addition in this circuit? Well, the new addition in this circuit is this block and this block. So let me erase the ink once again and explain these blocks only in some amount of greater detail. So instead of searching for a block inside all the entries, we only search for it within a given set of lines. That's the reason it's called a set associative cache. So each of these lines is called a way. So this particular set associative cache, one second. This particular set associative cache is called a four-way set associative cache, which means that any of the four ways or any of the four entries can contain the line. So we take the set index, which we again get from the address, and we access the set and in specific the four entries within the set. For each of them we combine. If there is a match, well, we get a hit, and also we find out which one matched. So if it's this line, that's fine. Then we choose the corresponding entry, which is this entry, and we use it to access the data array. So here is a mathematical look at it. So let the index be I and the number of elements in a set be k. So then the indices that we access is pretty much I times k plus I times k plus 1 till I times k plus k minus 1. We read all the tags in the set. We compare the tags with the tag obtained from the address. We then use an OR gate to compute a hit or miss. And finally, we use an encoder to find the index of the matched entry. After that, we read the corresponding entry from the block array. Furthermore, each entry in a set is known as a way. And if there are k blocks in a set, it's called a k-way set associative cache or a k-way associative cache. So before I go into the data read operation, I would like to look at this particular figure once again. And the best way to look is to erase what we had written earlier. So in this particular cache, what you would recall is, so let's take a look at the tag size. So tag is what is stored in the tag array. In the case of a direct mapped cache, the tag was only 19 bits, right? So in the case of a direct mapped cache, the tag was only 19 bits. In the case of a fully associative cache, the tag was 26 bits because we needed a larger tag. In the case of a set associative cache, the tag can vary between 26 and 19, and the reason being that we allocate some of the bits for the index, for the set index, for finding out which set, and the remaining bits become part of the tag because they are required to uniquely identify a block. Because the total block address is 26 bits, but we can use a part of the bits to first find the set, and essentially once that gets fixed, the remaining bits have to be used to compare with the tag array. So as we can see is that as we increase the number of sets, right? So the as we increase the number of sets, the tag will actually get smaller and smaller and smaller till you can't increase it beyond this point, which means that every set at this point contains one entry. Similarly, if we decrease the number of sets, then what will happen is that a tag will get larger and larger, and the index part will get smaller and smaller till we reach the fully associative point. At this point, a block can be there in any of the 128 entries of the cache. So there is no index. The entire thing, the entire cache is like one set. At this point, the tag becomes the largest, which is 26 bits. So the advantage again of this design is like this, that it is somewhere in between a fully associative cache and a direct mapped cache. So if you consider speed of operation, then clearly a direct mapped cache is the fastest, followed by a set associative cache, followed by a fully associative cache. Now if you consider the hit rate, we have the maximum amount of flexibility in a fully associative cache. We reduce the flexibility in a set associative cache and we further reduce it in a direct mapped cache. Alright? So as a result, so there is no hard and fast rule that in a particular situation, a particular kind of cache needs to be used. But as a general rule, people prefer the middle path, which is a set associative cache, with either a two-way or four-way, in some cases eight-way associativity. Alright, so now let's take a look at the data read operation. So this is a regular SRAM access into the data array. In some cases, the read and the lookup can be overlapped for a load access. So let's see how. So if we consider a set associative cache, what we can do is that we can, the first thing that we do is that we'll compute the index of the set. And if a set has four ways, we need to compare the tag with each of the, with contents of each of the ways in the tag array. Simultaneously, what we can do is that we can do a little bit of additional work. We can read the contents of all the four ways from the data array. So in this sense, we are overlapping the data read with the lookup. After that, once we compute the index of the matching tag, so let's assume that the third entry was the matching tag. Then the third entry of the data array is what can be chosen, right? So we can sort of overlap both. In a sense, we are doing additional work. Otherwise, what would we have done otherwise? We would have read all the four tag entries, done a comparison, found a match. Then for that particular match, we would have read the entry in the data array. Right? So let's say this is the tag array and this is the but now let's do some amount of additional work and let's read all the four entries of the data array and in parallel read and compare all the four entries of the tag array. If we find a match, we can then choose one of them, but at least the time for reading the data we could overlap. Now let's take a look at a write operation. So before we write a value, we need to ensure that the block is present in the cache. So most of the time students are not able to understand why is this the case or why should this be done. Well, look, if this is not done, so because students say, I'm going to write, so I'm going to write new data anyway. But there is a problem. The problem is that most of the time you're either writing 4 bytes if it's an int, you're writing 8 bytes if it's a long int or a double, But how large is a block? A block can be 32 or 64 bytes. And since a block we are treating as an indivisible unit, if we just, let's say, replace this part of the block with new data, well, we'll have to remember this somewhere. Maybe after this, we can have another write operation which will write to this part. So if that is done, we will need to maintain some amount of state somewhere to remember which part of the block was written when, right? And which parts are untouched and which parts are new. That's a lot of additional work. Also, it breaks our abstraction that a block is an atomic unit, right? So we have always had this neat and convenient abstraction that a block is like one indivisible unit. Hence, what we do is that if we have a miss, we first fetch the entire block, the old contents of the block. After that, we write the new data. So how do we do this? We write the new data. We also need to remember if new data was written to a block after it came to a cache. So we maintain a modified bit in the tag array. If a block has been written to after it was fetched into a cache, we set it to 1. Otherwise, by default, the entry remains a 0. But if you write to it, then yes, 0 becomes a 1. So there are two policies. One is write through and one is write back. So whenever we write to a cache, well, so because we have an inclusive cache hierarchy, any block which is present in the L1 cache, a block will also be present, the same block, the same address will be present in the L2 cache. However, the block in the L1 cache can have newer data. So there are two ways of handling this. One is write through and write back. So write through says that whenever we write to a cache, we also write to its lower level. And in the lower level, you'll have the block that is guaranteed by the property of inclusion. So this basically means that if I have a system like this with an L1 and an L2, I write to any block, I do a store to any block in L1, it gets propagated to the copy of the block in L2. So this has some advantages. One advantage is that I don't have to maintain a modified bit. Well, we need it in some cases, but in general, no. If I want to throw this block out of the cache, I can happily throw it, right? So we can sort of seamlessly evict data from the cache. So in that sense, for write through, actually, when you are doing a simple discussion, a modified bit is not required. But in the case of a write back, the idea is different. We do not write to the lower level. And also whenever we write, we set the modified bit to 1. So the advantage of write back over write through is that we are sort of reducing the number of accesses to the lower level. So let's assume that there are hundreds or thousands of accesses to the same block, right, in L1. If it's write through, every single access will go to L2. So that will waste a lot of power and create a lot of traffic to L2. What the write back cache instead would do is that you'll keep on writing to L1 and you'll just set the modified bit to 1. Nothing else. So in a write through cache, an advantage was I need to throw something out of L1, I can just throw it out. In the case of write back, it's slightly different. At the time of eviction of the line, eviction means when it's being thrown out, we need to check the value of the modified bit. If it's not modified, well, we can throw it out. If it is modified, we need to write it to the lower level, right? Such that the changes are at least there. Okay. So after write back and write through, where again, what is the trade-off? Actually, let me just go back one slide. The trade-off is that write through has far more traffic at the lower level, but evictions are cheap. Write back, the advantage is that traffic at the lower level is low, but evictions are expensive. Now let's take a look at the insert, replace, and evict operations. So if we don't find a block in a cache, we fetch it from the lower level. Then we insert the block in the cache with an insert operation. So let us add some new state. Let us add a valid bit to a tag. If the corresponding line in the data array is non-empty, which means there is some valid data, the valid bit is 1. Otherwise, it is 0. So what is the structure of a tag in a tag array now? We have the tag part of the address. We have a modified bit and a valid bit. So when we are inserting a line, let's say it's coming from the lower level, we check if any way in a set has an invalid line, which means its valid bit is 0. So the line is empty, the entry is empty basically. If there is one, then we write the fetch line to that location and set the valid bit to 1. So consider a 4-way associative cache which has 4 entries for each set. After mapping to a set, we find that the last entry is empty. So if any new line is coming that maps to this set, it can be put in the last entry. If that's not the case, we need to find a candidate for replacement, throw it out, which basically means evict, and insert in this new position. So replace operation means that we are searching for a candidate in a set for replacement. So a cache replacement scheme or replacement policy is basically to find one victim, right, in a set. So there can be many schemes. They have their pros and cons. So we can have a random replacement scheme where inside a set we can choose any of the ways at random, right? If all of them have valid data, choose any one. So recall that a fully associative cache is also a generalization of a set associative cache where the entire cache is one set. So the same schemes apply. So one solution is just at random choose any line and just throw it out. A disadvantage is that temporal locality is being hampered, and the reason that is happening is because maybe one of these lines is very frequently accessed, and if this gets thrown out, we'll have more misses. We can then have a FIFO replacement scheme where FIFO is first in, first out. So in this scheme, when we fetch a block, we'll assign it a counter value equal to 0. And for the rest of the ways, so we'll keep a counter with every way in the tag array. So when we fetch a block for the first time, we'll keep its counter as 0. And we'll increment the counters of the blocks in the rest of the ways in the set. So this will ensure that how do we know which block came the first? By the one that has the highest counter. So if you have a 3-bit counter, well, the counter can at best reach 7. But that's all right. We'll at least find one of the entries that is the oldest and we'll be able to throw it out. As mentioned on the previous slide, we choose the way with the highest counter for replacement. So let me give an example. Let's consider a 4-way associative cache with 4 entries. So assume that initially everything is empty and we bring in the first block. So it has a counter of 0. After that, we bring in one more block into this set. So that has a counter of 0 and this is incremented to 1. Then we bring in one more block. So we increment the rest of the counters, this to 1 and this to 2. Then again we bring in one more block. So we increment this to 0. This is 0 to 1, 1 to 2 and 2 to 3. Then it so happens that this block which we brought in, which is essentially the earliest, the oldest, is accessed extremely frequently, right? This block is extremely popular, so it's accessed extremely frequently. And then we try to bring in one more block into this set. The one that will get evicted is this block. But this is maybe the one that should not get evicted. And maybe this block was getting accessed extremely frequently. So this will violate the principle of temporal locality And so a line that is fetched early might be accessed very frequently. So this might not be the right thing to do. What we want to do instead is evict that line which has the least probability of being accessed in the future. There is no way of knowing what's going to happen in the future, but at least we should look back into the past and try to find a line which most likely will not access in the future, right? In the near future. So one such scheme is LRU, least recently used. So the idea here is that we replace the block that has been accessed the least in the recent past. So basically from the past we are trying to predict the future, right? From the past we are trying to predict the future. So what we do now is that we try to find that block which, let's say, in the recent past, right, or which was maybe accessed the least in the last 100 cycles or something like that. So this follows directly from the definition of stack distance, right? So we are essentially choosing a line which is the lowest in the stack, but we can't really maintain a stack. It would involve a lot of work. And it's not possible to do that with a limited number of bits in hardware, even though this approach has been proven to be optimal in some scenarios. So true LRU is hard. Let us instead implement something called a pseudo LRU, which in a sense gives us most of what LRU promises. So pseudo LRU is like this. Let us try to mark the most recently used elements. Something that is not most recently used, we can think of it as least recently used. So let us associate a 3-bit counter with every way. So we'll pretty much augment an entry in the tag array to have additional 3 bits. Whenever we access a line, we increment the counter and we'll stop incrementing beyond 7. So we'll assume that 7 plus 1 is equal to 7. Then what we do is that, so let me maybe, till this point show an example. So let's say that we have different lines, so they can have different counts. So then we access this line. So from 4 it will become 5. Then we access this line. It will become, from 2 it will become 3. We again access this, this will become 3. Again we access this becomes 4. We access this becomes 6, and so on. Then what we do, we periodically decrement all the counters in a set by 1. So periodically, every few 100 cycles or 1000 clock cycles, we decrement the counters by 1. So instead of 3643, we will replace it, right, with, instead of 3643, what will we have? We'll have 2, 5, 3 and 2. So why do we do this? Because if we don't do this, ultimately all the counters will reach 7 and remain at 7. After this, what we do is that whenever there's a new access, we'll keep on incrementing. Now let's say a new block comes. So if a new block comes, which one will we evict? Well, the one, we should evict the one with the smallest counter. This means that in the recent past, it has been accessed the least. So let's say there are 2 with a count value of 2. So let's try to evict this one. So when we throw this out, the question that remains is what should be the count of the new block? Well, the new block is the most latest. So it should have the highest priority as per temporal locality. So we'll set its counter to 7. Let's assume that after some time, maybe in the next 1000 cycles, none of these are accessed. So then gradually we will decrement their count by 1. So this will become 1, 4, 2 and 6. Then assume that we have some more accesses. So then the counts will keep increasing. So the logic here is that we always evict the block with the smallest counter. And that is because this means that in the recent past, this block has been accessed the least. Right? So if in the recent past it has been accessed the least, this means that even in the near future, we'll most likely not access it. But something that has been accessed quite a bit in the recent past, we will be accessing it also quite a bit in the near future. So that's the reason we don't evict it. And also we set the counter to 7, which is the highest we can for 3 bits for a newly fetched block. And the reason is that if a block is coming just new, we want to keep it for some time, right? As per the definition of temporal locality. So pseudo LRU is very popular. It is very commonly used, and it has a lot of benefits associated with it. So it is known to be one of the best replacement schemes. And the idea is very simple. We have a logic for incrementing. Whenever we access, we increment. Don't go beyond 7 in this case. Periodically, we decrement because unless we do that, all the counters will remain at 7. Whenever a block comes in, it comes in with the highest priority, which is 7. And for replacement, we choose the block with the lowest counter. And the lowest counter means in the past, it has hardly been accessed. Then we consider the evict operation. Well, this is very, very simple. If the cache is write through, nothing needs to be done. We can throw out the line. If the cache is write back and the modified bit is 0, nothing needs to be done. We can evict it. If the modified bit is 1, it means that new data has been written to this line. So we need to write the line to the lower level and then evict it. That's the only difference. Alright, so let's take a look at all of these operations in a diagrammatic fashion. That will hopefully clear up things. So let's take a look at the load operation, right? To load something. So we can do a lookup. So lookup essentially means that we access the set in the tag array, and we compare each entry in the tag array with the tag part of the address. So a part of this, particularly after computing the set index, a part of the lookup process can be overlapped with the data read operation, right? So this can be the period of overlap. And we have already discussed how we can get an overlap, right? And this, mind you, happens in the case of a hit, and this is what we do in the case of a miss. So let's discuss the case of a hit first. So in this case, once we have started the process of reading all the 4 tags in the 4-way associative cache, we can also read their corresponding data values from the data array, right? So we can start reading them in parallel. Even though all 4 will not be required, but that's okay. We are sort of trying to reduce the time. Once at the end of the lookup stage, we know whether it's a hit or miss. So if it's a hit and we know exactly which index has the data value, we can then, after the read finishes, choose that one. So at least by a little bit of overlap, we save some time. Instead, if there is a miss, then so basically we do a lookup in the lower level cache, we read the block, and then we insert it, right? And after inserting the block, it is possible, so these question marks indicate that it will not happen all the time, it can happen sometime. We find a candidate for replacement, right? One of the lines, and then we evict it. So if it's a write back cache, there is a necessity of there can be a necessity of writing it to the lower level if it's modified, and then again we insert the line that has come. After that, we again go to this stage where we, well, in this case, we know where exactly we put it, so we can issue a data read after this. I'm sorry. We don't have to actually go here. Oh, I'm sorry about that. I just take back what I said in the last 15 seconds. I'm sorry. Yeah, what we need to do is that we don't need to issue a data read because we already read the data from the lower level. So we don't need to read it once again from the higher level. So since you have read the data, the values are already available. So this can be passed as an output. All right. Fine. So let's take a look at a write operation in a write back cache. So in the case of a write operation, if there is a hit, we cannot have an overlap between lookup and data write, right? So that's not possible because otherwise, we can't write to all the 4 data blocks, right? We'll end up corrupting at least 3. So the right approach is that we do a lookup first. If the data is there, we address the right entry in the data array and we do a write to it. Similarly, however, if there is a miss, then we do a lookup in the lower level cache. We get the block and we try to write the block. So the way that we try to write the block is something like this, that we first insert it, right? So first write the block, which basically means that the new data that we want to write is written to the block that we read from the lower level. And then we try to insert the block with the new contents into the cache. If we find a place to insert, well and good. Otherwise, we need to follow the replace, evict, insert, this sequence of 3 operations. So we find a candidate for replacement, we evict it, and so there can be a necessity of writing it to the lower level also because it's a write back cache, and then we insert the new line. If it's a write through cache, something else needs to be done. So if it's a write through cache, well, this part remains the same. In the case of a hit, we do a lookup and a data write, but we also send the write to the lower level, right? So this is what was, if you look back at the previous slide, this was not happening over here. But in the case of a write through cache, whenever we write, we need to send it to the lower level. If there is a miss, what we do is that we do a lookup in the lower level cache, we get the block, we write the new contents to the block, right? So whatever integer or float or double, whatever we wanted to write, and the new contents of the block are once again written to the lower level cache. And also at the same time, we try to insert it in the upper level cache. We find a place, well and good. Otherwise, we need to do a replace, the sequence of replace, evict, and insert operations. So note that in this replace, evict, insert sequence, nothing needs to be done. We don't need to access the lower level cache. And the reason is that this is a write through cache. So we don't have any lines in the upper level which have any modified data, right? So the modified bit essentially for all write through cache lines is 0. So this is essentially because we have written the block at the time of, at an earlier point of time, which is this point to the lower level.